Welcome. In this video, we will solve the bank loan case. This will be a real practical hands-on exercise, and I assume that you already have watched all the prior videos. These include touching data video, analyzing patterns with pivot tables, iris data video, and the introduction to Azure Machine Learning Studio. Otherwise, you will not be able to follow this video. Now in this video, we will first upload the processed bank loan data to Azure. As a short recap, the processed bank loan data was the one that we already cleaned for you. So there shouldn't be any big issues with the data quality in this version. Now in this video, we will be setting up a much more general experiment. Now this will also include treating missing values and also comparing different kinds of models. We will also have to tell Azure that we have categorical variables. We will have to use a separate module to do this. We will also briefly discuss stratified sampling and take a closer look this time at the confusion matrix. A big part will also be choosing among different kinds of models. So what kind of algorithm should I choose at the end? Which algorithm should I start with? What are the differences to different kinds of algorithms, and are there any best practices? At the end of the video, we will also investigate using an Azure module what variables could be the most important in our dataset. Let us quickly recap the bank loan case. What is it about? Now, we have data on past customers and whether or not they paid back their loan. So our Y variable of interest is the loan status. That's a binary variable, either 1 when the customer defaulted on the loan and was not able to pay back, and 0 when the customer was able to pay back the loan. Our X variables include information on the customer, such as his annual income, the current loan amount, the credit score, or the purpose for the loan. Now in the prior video, we already were able to observe some interesting patterns using the pivot tables and the charts. These patterns, for instance, included that people who default on their loans have a lower average annual income, have a higher current loan amount, have a lower credit score on average, and that roughly 80% of all defaulted loans were due to debt consolidation. Now, the Chief Risk Officer wants us to build a predictive model that can identify whether or not a customer will be able to pay back the loan. On the one hand, we therefore want to classify future loan applications into good and bad risks, and on the other hand, we want to monitor outstanding loans. For instance, if we have updated information about a client, this could be reflected in his risk to default, and we could take timely countermeasures. Let's proceed by downloading the data. We click on the link on here. This forwards us to the OneDrive folder where we can download the data in the bank loans folder. Now this time we want to download the comma-separated value file, the .csv file, which is called loan defaults _processed. This is the data that we cleaned for you for the missing values and the inconsistencies. Click in the upper right corner and download the data. After you log on to studio.azureml.net, you'll be greeted with the Experiments tab home screen. Now note that we are using a custom dataset which we prepare for you, and it's not available on Azure Machine Learning Studio. We will have to upload it manually. To do this, we switch to the Datasets tab here on the left-hand side and click on the plus sign, New, in the bottom left corner. We then select Upload from Local File, choose File, and select the loan defaults _process.csv file. When you're greeted with this message here, the upload is completed and you can click OK. Now the next step is, of course, to create a new experiment. We click on the Experiments tab and click on New and a blank experiment. This gives us now a new experiment where we can conduct our bank clone case in it. We can give this experiment now a name, for instance, my bank clone dataset. We can now drag and drop our newly uploaded data inside the experiment. So we have the newly uploaded data in the left-hand side under My Datasets, and here the lone defaults underline process.csv data. Now, what I always recommend you to do as a first task is to look at the data you just uploaded. Maybe you will find some mistakes and you will have to amend it in the step before. To do this, we right-click on this dataset node and this output node here and visualize the dataset. We can see here on the top that we have almost 200,000 rows with 17 columns. Well, you can also observe now that we already removed the two identifying variables for you because we will not need it for this prediction exercise. If you compare the variable names here in this dataset we just uploaded, you will also find that we replaced the blanks by underscores. Now, why did we do this? The reason is actually quite a technical one because a lot of programming languages, they don't like blanks. So it's good best practice to avoid potential problems by just removing them beforehand. What we can also see here from the lone status is that we have, this is our y variable. It has two values, two unique values, and a 0 and 1. So 1 being the case that the loan defaulted and 0 that it was paid back. What we can also observe here from this sort of frequency bar is that we have 69% of the cases are non-defaults and 31% of our data points are marked as default. What I always suggest you do as a first exercise after opening the dataset is that you go through each and every variable and you check what type of variable it is. So here on the bottom we have the feature type. So what kind of variable is it? Is it numeric or is it a string variable? String variable, for instance, we have here on term, string feature, and we can look at these different levels of the categorical variable. So we have a short term and we have long term. Sometimes by doing this you will find that you forgot to clean missing data. For instance, you could see that you forgot to remove the NAs. These NAs would be coded as a string. So you would have to go one step back, go to the Excel file and replace all the cells with an NA inside with a missing value. That means just a blank. Now, before we go on to the modeling exercise, I would like to just briefly spend some words on the other variable, which is quite confusing a bit. This is the years in current job variable. Now, if you look at this variable, if you recall that in the Excel file, it looked quite a bit differently, right? So now we have a numeric feature. But if we compare it with the Excel file, we see a completely different picture. We have 10 plus years, 4 years, 10 plus years. Here we have an NA, which we obviously removed for you. And we also have smaller than 1 year. So what we did here is that we replaced these years. Just we cut off the years and the 10 plus, we omitted the plus, and we simply kept the numeric values. What we also did is if it's smaller than 1 year, we replaced it by 0.5. This numeric recoding makes it quite a bit easier to handle the data when modeling. We could have also just read it in as it is, but some programs also, they experience troubles when having these special characters like a smaller sign or a plus. So what I want to tell you at the end is that even though we have a numeric feature in years in current job, it actually is a categorical variable, but Azure still doesn't know it, and we need to tell it in the next step. Now, just by scrolling through and observing what kind of variables we have and recalling from the past videos what kind of variables the data has, we know that we have 4 categorical variables. One of them is term, the other one is years in current job, the other one is home ownership, and the last one is the purpose variable. What is also very important is that you go through each variable you have in your dataset and you check for missing values. You can do so very easily in Azure by just clicking on the variable, and you will see missing values. So for the monthly debt variable, for instance, we have 0 missing values. Let's get started with exercise number 4. The goal of this exercise is that you'll be able to train your own classifier. So a classifier of your own choice. You will select an algorithm, and then you will be able to evaluate that algorithm by using the ROC curve, so the receiver operator characteristic, and by looking at the confusion matrix. The first step will be is to identify your factor variables. We already briefly discussed, so we have 4 factor variables in our dataset. You will then have to tell Azure that these variables are indeed categorical. You can do so by using the edit metadata module. In a third step, I ask of you that you go back again and you check all your variables for missing values, and you will observe one of the variables has very, very many missing values. Now, due to the fact that there are that many missing values, I just suggest that we just remove that variable from our analysis so that our final estimation dataset will not include that column. You can deselect columns in the select columns in dataset module. Now, we still have some missing values in rows. So in the 4th step, I ask of you that you remove the rows with missing values. You can simply do so by dragging and dropping in the clean missing data module, and then you click on the module, and on the right hand side you will see some options, and there you can simply select the option that you want to remove those rows. Now the 5th step is that you on yourself choose one classifier, and that you get to the step that you are able to inspect the ROC curve. So just like we learned in prior videos, you will have to organize all these modules in a workflow, and if everything goes right in the end, you can simply right-click on the output node of the evaluate model module, and you will be able to observe the ROC curve and the confusion matrix without problem. I therefore ask of you now that you quickly pause the video and you try to solve this exercise on your own first. After that, we will discuss a possible solution. Let's start with the analysis. We start by telling Azure what our categorical variables are. We do so by dragging and dropping the edit metadata module in from the side. We connect the nodes and we launch the column selector. As we discussed, the term is a categorical variable, years in current job, home ownership, and the purpose. We now need to tell this module that it should change these variables, so term, years in current job, home ownership, and purpose, the data type to string, in particular for the years in current job, because that was coded as a numeric, and that it should make all of them into a categorical variable. We now proceed by deselecting, that means omitting that column from our analysis that featured many missing values. Which variable it is, we can just go back to our data, visualize it, and go through the variables to see which one has the most missing values. So the one I'm referring to is months since last delinquent. You can see it has 106,000 missing values out of 195,000 possible values. So this is quite a lot, and it makes no sense including this variable in our analysis. We would lose too many observations. We can deselect columns or omit columns by using the select columns in dataset module. And we exclude. So we start with all columns and we exclude months since last delinquent. Let's proceed to missing values. So we still have missing values in our data. And I told you one option is simply to remove those rows. We can do so using the clean missing data module. Now here in the cleaning mode, we can tell it to either we could replace it with other values. So for instance, the mean, median, or mode, or we could impute it using mice. That's an algorithm which imputes values, so it finds a reasonable value based on the other covariates, so on the other x variables. But in this instance, we'll simply just remove the entire row. Now, it's always a really good idea to visualize your final cleaned data in order to see if there were any mistakes in your workflow. We can do so by just running the project. So we can now visualize the cleaned data by going to the clean missing data module, right-clicking on clean dataset, and visualizing. What we now see is we have 16 columns instead of 17, and that variable with many missing values is not around anymore. Now we also see here we excluded other observations due to their having missing values, so the sample reduced from 196,000 to 152,000. This is always a really good check to do, and you should always do it. Now let's continue by actually starting the machine learning workflow. The first step is always to split the data into training and testing data. So we train the model on the training data, and then we keep out a sample which will be used to test the model on later. So the model has not seen the testing data. This is very important in order to avoid overfitting. So if we click on the split data module, we also have the option to do a stratified split. We can select this on true. And now we need to tell it which column should be stratified upon. In our case, this is obviously the loan status. So what does a stratified split do? It just makes sure that in both the splits, so in the training and testing data, there is the same percentage of default observations. This is really important if you have very few default observations, since you don't want to have all your default observations in the training data and to have no default observations in the testing data. And you can make sure that you have an equal distribution of the default points in both splits. That's why you should use this sample splitting with the stratified split option, especially if you have a low percentage of defaults in your data. So we, for instance, have now 31%, but I still think it's a good idea as to avoid any unnecessary fluctuation. Now, what we can also do is fraction of the rows in the first output dataset, that is the training dataset. We can just tell it now, for instance, 70%. So 70% of our data goes into the training of the model, and 30% of the data is set aside for testing the model later on. We now drag and drop in the other necessary components in order to perform the machine learning task. This is the train model module, the score model, and the evaluate model. Now, I always recommend you to first start with a very basic algorithm. A basic algorithm that also doesn't need much intervention by the researcher. So that means you don't need to select specific parameters for the model. And for a binary choice, the usual first model which is applied is a logistic regression. And then one just looks at the ROC curves, at the confusion matrix, and decides upon that and just compares it with other more complicated models whether or not there is any improvement. So in this case, we selected 2-class logistic regression as our first model, which we will investigate. Now in the train module, we also have to select which column is our y variable. So now we have all the steps necessary in order to make a first prediction. We can run the complete model just by hitting run. We can now look at the ROC curve and the confusion matrix by simply going to the evaluate model module, right-clicking on the evaluation results and click visualize. Just by taking a first look at the evaluation results, we see here that we have the ROC curve, so the receiver operator characteristic. And if we scroll down, below we have the confusion matrix here. Here we have a couple of metrics which indicate how good our classification was. We will discuss now all these metrics and the confusion matrix and the ROC curve now in detail. Now we all saw the output of the evaluate model module a couple of times in prior videos, but I still think because it's such an important topic, we should discuss it a bit further. The most important thing that you should take away from the ROC curve is that it shows graphically the relationship between two errors. Those two errors are, on the one hand, the true positive rate, that is also often called the recall or the sensitivity, and on the other hand, it's the false positive rate. Now in classification, positive simply refers to the fact that we have a 1 in our loan status variable. So that means that the loan defaulted, that the applicant, he was later not able to pay back the loan. A negative, on the other hand, is simply a 0 in the loan status variable and indicates that the loan was paid back. True positives are when we predicted that a loan would default and it actually did default. So our prediction was correct. The true positive rate just measures the share of defaults we predicted correctly, or how many defaults out of total defaults were we able to catch. False positives, on the other hand, are that we predicted a loan would default, but in fact it did not default, so we made an error. The false positive rate just measures the share of non-defaults we did not predict correctly. So now what do these two errors actually mean for the HSG Bank? If we have a high true positive rate, this means that the HSG Bank suffers few defaults. So the Chief Risk Officer is happy. On the other hand, if we have a low true positive rate, we are not able to catch as many defaults with our model, and the HSG Bank suffers many defaults. This will of course be very negative for the HSG Bank. Now concerning the false positive rate, if we have a high false positive rate, the HSG Bank turns down many prospective clients. So we are missing out on prospective clients which would pay us money, but we think they will default, and that's why we don't give them money, even though they wouldn't default. On the other hand, if we have a low false positive rate, the HSG Bank can give many prospective clients loans because we only have few false positives. So at the end of the day, it really boils down to the question, is it costlier for the HSG Bank to suffer some defaults, so that would refer to the true positive rate, or to miss out on prospective clients, that would refer to the false positive rate? So what we have is a trade-off. In prediction exercises, we cannot have a very, very, very high recall without having a couple of false positives. There are always going to be mistakes when we predict something. So the perfect ROC curve would be indicated here by just a vertical line on the recall, right? So we would have a 100% recall and 0 false positives. This would be the absolute best ROC curve possible. Now what we could do in our sample is just to say all our data points, all our loans will default. So in our predictions, we would only have ones. What would this mean? This would mean that we would have a true positive rate of 100%, so we can catch all defaults because we label simply all observations as defaulted. But this would also mean that we would have a false positive rate of 100%. So we make a lot of false positives in that case. This would give us this point here in the upper right corner. Now, on the other hand, what we could also do is we could simply say that all our loans will be paid back, right? So a 0. That means we would have a true positive rate of 0. We are not catching any defaults because we label all observations, all loans as non-defaulted. But this would also have the implication that we would have a 0 false positive rate. So we don't make any false positives because we don't label anything as positive. The same argument can be applied to other cutoff points, which we use to decide which observations get to be classified as defaults versus non-defaults. And what we get at the end is simply this 45-degree line. Now this 45-degree line simply indicates random guessing. So if our model has a ROC curve, for instance the blue one, which we estimated now with the logistic regression, if this is above the 45-degree line, our model is better than random guessing. So this is quite nice. And if it's not better than random guessing, you should throw away the model, of course. This also means that if we have two different kinds of models, and one model has for a given false positive rate a higher true positive rate, then with fewer mistakes we are able to catch more actual defaults. This would mean that this model therefore is better. So given the same false positive rate, we're able to catch more defaults. This is a win. So this means if we have two models and one of the ROC curves is above the other ROC curve, we would prefer, of course, that model with the higher ROC curve. So the ROC curves can really also be useful in model selection, or which algorithm we should choose for our particular business question. Now finally, you know that we are interested only in the prediction quality on our testing dataset because we simply use the training dataset to estimate the model. This also means that, of course, the ROC curve, it is computed on the testing dataset, which the model did not see while being estimated. So now, what is the confusion matrix? The confusion matrix is simply a snapshot of the ROC curve for one particular probability cutoff. Now in our example here, and most commonly, the cutoff is simply 50%. So all observations which have a probability to default above 0.5 are classified as default, so as a 1. All observations below 0.5 are classified as non-defaulted. In Azure, you can simply move this lever here back and forth to increase or decrease the probability threshold. As you do so, you will see that the confusion matrix, it always also changes. So the ROC curve is simply just calculated from the confusion matrix at the given probability cutoff. Now, if we do binary classification, we have 4 outcomes which are possible. These are just indicated here in this 2x2 matrix, which is called the confusion matrix. So if we predict that our loan will default, and in fact it really defaulted, that's called a true positive. If we predicted that the loan will not default, and in reality it really didn't default, this is called a true negative. Now, our 2 mistakes we can make are the false positives and the false negatives here on the diagonal. The false positives are simply, we predicted that the loan will default, but in fact it did not default. The false negative, on the other hand, is we predicted it will not default, but in fact it actually did default. Now, to assess how good our predictions actually are, there are a couple of evaluation metrics used. These include the accuracy, which is depicted here, the recall, which is simply the true positive rate, and the precision. Now, the accuracy answers the question on how good is our forecasting ability of both defaults and non-defaults. It is simply calculated by our true positives, so the sum of the true positives and the true negatives, divided by all these entries here, so by the total sample size. The recall, on the other hand, it answers the question on how good is our ability to detect defaults. And it is simply calculated by the true positives divided by true positives plus false negatives, so by the total defaults. Total defaults are simply true positives plus false negatives. The last really important evaluation metric is the precision. The precision answers the question how many of our positive predictions are correct. In the matrix, this is simply depicted by our predictions. So if we predict a default, how many of those defaults were actually correct? So that will be the true positives here divided by the true positives and the false positives. So in our case now with the simple logistic model, 2/3 of defaults and non-default predictions were correct. Furthermore, we were able to catch a total of roughly 31%, 32% of all defaults. We were able to do so by having a precision of 62%. This means that out of 10 positive predictions, 6 were actually correct. Now, as you vary the threshold here, back and forth, you will see that these numbers change, and the question is, where should I set the threshold? The F1 score, it tries to give like some kind of metric, what kind of threshold could be chosen. The F1 score is simply just a harmonic mean between the recall and the precision. So it tries to make some kind of trade-off. But as I already mentioned, decision makers in the business actually need to decide this threshold because only they can really estimate how important and how relevant these 2 errors actually are for the business. So whether or not it's more important to suffer defaults, so that will be the first error, or that we turn down prospective clients because we think they will default even though they do not default. That will be the second error. So with a high recall, we can catch many defaults, so the HSG bank loses less money. With a high precision, we can avoid missing out with not giving prospective clients money. Now, to sum things up, let's check on the ROC curve where we are if we choose a threshold of 50%. Now we can see that the threshold of 50% indicates that we have a recall of 31%. The recall is also just the true positive rate. So here we have the ROC curve, and the true positive rate in our case with the probability threshold cutoff of 50% is here. So you see, we are here on the ROC curve. Now we need to question ourselves if this is the right choice, because we could also obtain all these other choices simply by changing the probability cutoff threshold. Alas, goodness of the model, or how good the ROC curve is simply the area under the curve. The area under the curve parameter is just the sum of this whole area. So the perfect ROC curve would have an area under the curve metric of 1, because 1 times 1, right? We see below that we have an area under the curve of 0.7. So when comparing two different kinds of ROC curves, the one with the higher area under the curve is generally also located above the other ROC curve and is thus preferable. Now, next to providing a very clean interface and a very organized workflow in order to do machine learning experiments, what I think one of the best functions of Microsoft Azure Machine Learning Studio is that you can very, very easily compare different algorithms. If you remember, the Evaluate Model module has two input nodes. So we only use one now. That means that we can estimate a second algorithm and input its results into the second node of the Evaluate Model module. The result will be that here on this chart here, we will see a second ROC curve. The second ROC curve will be red. So the one of the first model, here the logistic regression, will be blue, and our second model, to which we compare it to, will have a red ROC curve. Now let's estimate a second algorithm on the same data. We can very conveniently click on a module and shift and click again in order to copy the modules. We can do now is simply click Ctrl and C and Ctrl and V to copy modules. We now only have to connect the nodes. So from split data, this is the training data set into the train model. The testing data set we put into the score model. The score model we can then put into the second input node of the Evaluate Model module. What we need now is a second algorithm. You can just simply type toClass, and here you have a list of different algorithms. I will just use a toClass decision force, for example. And we are done. Now we just have to run the whole experiment. After the experiment has finished running, we can simply get a look at the ROC curves by right-clicking again on Evaluation Results in the Evaluate Model module. What we see now is that we have the scored dataset, which is the one from the model, which was the logistic regression. So we estimated the default probability of the loans using a logistic regression, here with the blue ROC curve, and here with the red ROC curve, we estimated the default probability of the loans using a decision forest. So what we see now is that using a decision forest is much better than simply using a logistic regression. We can see so by, for a fixed false positive rate, we have a much higher true positive rate. So for given mistakes, we can detect more defaults. This is quite nice, and we should consider using a decision forest instead of simply a logistic regression. Forests are quite a nice algorithm because they require very little specifications beforehand. So before running the algorithm, you need to specify very few parameters. Forests also have the advantage that they also implicitly do variable selection. What they also can do implicitly is to learn non-linearities, which is quite nice. Other more advanced algorithms, such as neural networks or boosted trees, for example, they need to have a lot of parameters in order to be able to run the model. These parameters can be quite sensitive. Microsoft has already given you some starting values for these parameters, but if you conduct a deep analysis and you want to go live with this model, you should try to test out whether or not the model is sensitive to those starting parameters. Azure also has a module called Tune Hyperparameters module, which can help you in selecting optimal parameters. Now, the last question I would like to address in this video is whether or not you can identify very influential variables. So which variables are very important for your classification success? We can do so by using a module from Azure, which is called permutation feature importance. And this module, what this does, it just checks for each column. So for each x variable, it randomly shuffles all the values in that x variable. And then it compares whether or not there was a performance decrease. So quite influential variables, they should have a big change in performance, because obviously those values in that variable are important. By clicking on the permutation feature importance module, we can then select which metric it should investigate. So the effect on which metric. Now, for example, we have a classification, so we can be interested in our ability to catch the defaults, so the recall, or the true positive rate. We can then check the nodes, so the trained model. And what we need here is the test data. So from the trained model, it shuffles the x variables in each column, and then it checks its performance on the test data. Those variables with the biggest change, they should be the most important because their x values of that particular variable indeed do have some forecasting performance. Or said otherwise, that they affect its performance in, for example, calculating the recall on the test data. So the only thing left to do is to rerun the model. Now we can check the most influential variables by examining the results of the feature importance. What we see is that the credit score has the highest feature importance. The annual income is also very highly scored. Then we also have the monthly debt. This is quite intuitive, so we already saw the patterns while analyzing the data with the pivot tables. And we saw that applicants who defaulted later on their debt, on average, had a lower credit score. We also saw that they had a lower average annual income. So these results make quite sense. What also makes sense is that these variables here at the end, which had not so much variation in their variables, for example, bankruptcies or tax liens, they don't have a very high feature importance, so probably omitting them will not impact results. Now let's sum up this lesson quickly by just noting some quick key takeaways. First of all, you need to know your data, which variables are numeric or categorical, and need to treat them accordingly. You also need to watch out for missing values. If you have a minority class, so default observations are rare, it makes sense to stratify the sample while splitting it. One of the common splits is a 70-30 sample split. Now, as a general recommendation, first start off with a simple algorithm and see how it goes from there. It's always important to compare a couple of different algorithms against each other. But just be aware that more complicated algorithms, they need also quite some help in the beginning with setting some sensible starting parameters. Azure can help you here with some specific modules. We saw that the ROC curve is made up by just varying the probability threshold, and you should always set its size according to business decisions and weighing the two errors you can make against each other. Thank you for watching.